Hello everyone, welcome you all. In today's lecture, we will discuss precise mathematical definition of limit, that is also called epsilon delta definition. And after that, we'll look at few examples also. So till now, if you have any confusion about epsilon delta definition of limit, don't worry. By the end of this lecture, you will be absolutely clear. Let's begin. Earlier we have defined the definition of limit as limit extending to x naught fx equal to L. It means fx gets close to L, some number L, as x gets close to x naught. But real question is how much close? If we define closeness of the function value to L, so function may be here, okay? So this is a distance between function value fx and L, or function may be here a little closer to L, or it may be here much closer than before. Okay, same for if we define closeness of the variable x to x naught. So x could be here, okay, a bit away from x naught, or x could be here, okay, slightly closer, or x may be here extremely close to x naught. Okay, so what does close actually mean? How do we measure the term close? Here close is a vague term. Okay, so mathematicians answered these questions using two symbols. One is epsilon and second is delta. These two symbols helped us to quantify the vague term closeness. Okay, so if question is how close we want fx to be to L, so answer is within epsilon distance from L. Mathematically, we can write modulus of fx minus L less than epsilon. That can be written as L minus epsilon less than fx less than L plus epsilon. So function lies between L minus epsilon and L plus epsilon. Okay, vertically means it will be within epsilon distance above or below to L. Now second question is how close x must be to x naught to make that happen. That happen means modulus of fx minus L less than L. So for what values of x this inequality is satisfied? So answer is within delta distance from x naught. Okay, that means we can write mathematically we can write modulus x minus x naught less than delta, or we can write x naught minus delta less than x naught plus delta. Means whenever x lies within delta distance close to x naught, the function value automatically lies within epsilon distance from L. So definition of limit in terms of epsilon and delta is called precise definition of limit, because using these symbols epsilon and delta, we have removed the vagueness, closeness here. Okay. What is epsilon delta definition of a limit? Let fx be a function which is defined in some open interval about x naught, except possibly at x naught itself. Except possibly at x naught means function may or may not be defined exactly at x naught. You know, in limits we are always interested in how function behaves as x approaches to x naught, either from left or right, not necessarily what happens exactly at x naught. Now, what is the meaning of this complicated looking statement? See, limit of function fx as x approaches to x naught is L if for every small positive number epsilon, there exists a corresponding positive number delta such that whenever x lies within delta distance from x naught, the values of function lies within epsilon distance from L. Okay, so here this number epsilon represents how close we want fx to L, and delta represents how close x needs to x naught. In simple words, we can say the gap between fx and L can be made as small as we want by keeping x close enough to x naught. So this inequality implies that fx lies between L minus epsilon to L plus epsilon, and inequality for x implies that x lies between x naught minus delta to x naught plus delta. See here also, the function values fx lies inside the vertical range from L minus epsilon to L plus epsilon. Means fx may be here or maybe here, here. Okay. So inside this vertical range. And you see this vertical range is symmetric about L. Okay. Now for x, you see here, x lying between x naught minus delta to x naught plus delta. This is a symmetric interval, symmetric about x naught. Okay. But here x is not equal to x naught. We say limit of function fx is L as x approaches to x naught if for each epsilon we can find a corresponding delta such that keeping x within this interval, this symmetric interval will keep the function values fx within L minus epsilon to L plus epsilon. Let's take a simple example to see how epsilon and delta are related to each other. Suppose epsilon is 1 by 10. That means we want function values within this range from L minus 1 by 10 to L plus 1 by 10. Now we draw two horizontal lines, one at L minus 1 by 10 and other at L plus 1 by 10. This creates a small band where we want function values to stay. You can see that this epsilon band is symmetric about y equal to L. Now we find the values of x for which function values lies within this epsilon band. See here, this epsilon band for function values is corresponding to the interval AB. Okay. Here f of A equal to, you can see L minus 1 by 10 and f of B equal to L plus 1 by 10. Okay. So this is f of B. Okay. You can see this interval AB is not symmetric about x naught. So to get symmetric delta interval x naught minus delta to x naught plus delta, we choose delta as delta equal to minimum of absolute values x naught minus A, x naught minus B. Okay. So means this is x naught minus delta, this is x naught plus delta, which is equal to b. Now for epsilon equal to 1 by 10, we find a corresponding delta, this one, such that keeping x within this interval will keep the function values within this range. Okay, L minus 1 by 10 to L plus 1 by 10. Now we consider epsilon 1 by 1000, which is smaller than previous one. Okay, then epsilon band around L also becomes extremely thin. You can see here. So now we find the values of x for which function values lying within this range. See here, this is a, this is b, and you can see here f of a equal to L minus 1 by 1000, and f of b is L plus 1 by 1000. Interval AB is not symmetric, so to find symmetric interval which is inside this interval AB, means x naught minus delta to x naught plus delta is subset of AB. How to find delta? We write delta is minimum of absolute values x naught minus a, x naught minus b. Okay, in similar way for epsilon equal to 1 by 10. So this is delta. So now you can see that for this epsilon we are getting corresponding delta, this one, such that keeping x values inside this interval will keep the function values within this range. Okay, so to keep function values inside this narrow band, we have to keep x closer to x naught, means delta also becomes smaller. This shows how epsilon and delta depend on each other. Smaller epsilon means smaller delta. If you found this helpful, please like this video, subscribe to my channel and share. Thanks for watching. See you in the next one.